Okay, let's move on. The first thing that I wanted to say is that we have another exam upcoming next Monday. So this means that this class will be the last class that will be included in the second exam. And we'll finish up the coordination numbers today and then start with isomerism. But I won't test anything about isomerism anymore on the exam. So only the subchapter about coordination numbers will be tested. So in the last class, we discussed low coordination numbers and intermediate coordination numbers. So the low coordination numbers are the coordination numbers 1, 2, and 3. They are pretty rare. The intermediate coordination numbers are the numbers 4, 5, and 6. So these are pretty common, especially the coordination numbers 4 and 6. And today I would like to discuss high coordination numbers. So these are all coordination numbers of 7 and larger. So these are again less common in general, and typically they require a combination of a large transition metal ion and relatively small ligands around. Only under those circumstances the steric requirements are such that these coordination numbers can be realized. So let's start with the coordination number of 7. So like for the coordination number 5, there's actually no clear preferred structure associated with the coordination number 7. So we have in this case 3 structures which are approximately equally common. So the first one is the pentagonal pyramid. And an example for that is, for instance, heptafluorocirconate 3-. So the pentagonal pyramid is easy to understand. We have a pentagonal plane with 5 ligands, which you see here, and we have 2 additional ligands that cap that plane, making a pentagonal bipyramid. So the second possible structure, which occurs relatively often, is the so-called capped trigonal prism. So an example for that is, for instance, the heptafluorotantalate 2-. So in this case, you have 6 ligands that form a prism. You see this here. So 3 ligands form the first triangle, and here 3 other ligands form the second triangle, and then the 7th ligand is placed above the square here, one of the squares, made by 4 ligands that belong to different triangles. So 2 ligands belong to the first triangular face, and the other 2 ligands belong to the other triangular face. So can you imagine as to why the 7th ligand is actually on top of the square face and not on top of one of the 2 triangular faces?
It's just one of those spaces.
Yeah, there's just more space. So the square face is just larger, and the ligands have a greater distance from each other, and therefore the 7th ligand can more easily coordinate to the central metal atom. All right, then we have another possibility, and that's the capped octahedron. So in this case, 6 ligands make an octahedron, and the 7th ligand is placed on top of one triangular face. So an example is shown here. So this is a tetracarbonyl tribromo tetracarbonyl tungsten minus Ni, and you see here that we have 3 bromo ligands that lie on one triangular face, And then we have 3 carbonyl ligands here and here that lie on the opposite triangular face, which is actually oriented in a staggered orientation relative to the first triangular face, and then the 7th ligand sits on top of the triangular face where the carbonyl ligands lie. So now we could again think about, well, what's actually the symmetry or the point group? Can anybody maybe see what symmetry this molecule has? Imagine an octahedron in which we have an additional ligand above the center of one of the triangular faces. Also, virtual students are encouraged to make suggestions either by using the chat function. You can also unmute yourself and speak directly into your microphone. We will be able to hear you. Always useful to think first about where the principal axis is. And that's already usually half of the work. That's the biggest step forward. Anyone identify the principal axis? Can we first agree on that? All right, maybe I can help you a little. So the point group is C3b. Yeah, so we have the C3 axis as the principal axis, and it actually goes exactly for this carbon tungsten bond. Yeah. So we do not have a horizontal mirror plane, but we have actually 3 vertical mirror planes, and that's because when you imagine that this triangle here and this opposite triangle here are in eclipsed, in a staggered fashion, you can actually draw 3 vertical mirror planes that contain the principal axis. Okay, that makes the point group C3V. Okay, so one additional comment is that, like for the coordination number of 5, the ligands are, in this case, also not symmetrically equal. Okay, so in this case here, for the pentagonal bipyramid, we distinguish again between axial and equatorial ligands. So here, for the cat trigonal prism, we have actually 3 different kinds of ligands. So the 7th ligand, of course, is separate, but here we have these 4, okay, that are rotated in this case by a 4-fold axis. But in addition to that, we also have these two here. Okay, so in this case, of course, we have this carbonyl ligand here, and then we have here these 3 carbonyls and these 3 bromines on non-equivalent positions. Okay, then let's move from the coordination number 7 to the coordination number 8. So the most simple shape you can imagine for the coordination number 8 is a cube. Okay, the metal ion would sit in the center of a cube. However, this structure is not realized in nature for molecular compounds, and this is because there is a related structure which is energetically actually always more favorable. And this is the square entiprism, which is shown here. So what is the relationship between the cube and the square entiprism? The relationship is that 2 square faces are twisted by 45 degrees relative to each other. So in the cube, you see that this blue square here and this green square over there, they are in eclipsed orientation. But I can rotate the green square here by 45 degrees, and then my cube becomes a square entiprism. So these additional square faces here, see those? The other 4 square faces of the cube, they become triangular faces. Okay, you see one, for instance, here, and here, and here, and here. Okay, so an example for a square entiprism is the tetraoxalato zirconate 4 minus. So I have actually prepared a little video, which actually was a part of your textbook, that actually shows the interconversion of a cube in a square entiprism. And I briefly wanted to show you that video also on that occasion. That's not what I wanted. So now we see here, we start out with a cube, and we rotate one of the squares by 45 degrees, and we see our cube turns into square entiprism. Okay, maybe see it one more time. Okay, so now let's switch this back. Okay, so now there's another structure which is fairly common, and this is a dodecahedron. Note that this is not the dodecahedron we have discussed before, so it's not the Platonic solid. It is another polyhedron which has 12 triangular faces. And that dodecahedron is actually related to the square entaprism, what can viewed as a further distorted square entaprism. And it is actually shown here on this right side here. And you see that we have here this distorted square made of these blue edges, and we see here a green distorted square made of another 4 edges. So when I actually take my square prism and actually try to squeeze 2 opposite corners, okay, then this square becomes this distorted square, and when I actually squeeze 2 of the 2 balls from the green square together, then it becomes actually this distorted green square. And I've also made a little video about that. And just want to show you this as well. So we start out from the square entaprism. And now we squeeze the 2 green squares, the green square this way. Okay. And next we squeeze the blue square. Okay. And that creates essentially triangular faces. Okay. And now we can just show that they are triangular faces by placing the respective edges into the resulting polyhedron. Now our dodecahedron is finished. Okay, so this is how a square entaprism converts into a dodecahedron. Okay, so let us go from the coordination number 8 to the coordination number 9. So one example for this is a tri-capped entaprism, and a practical example for a tri-capped entaprism is the nona hydridorenate 2-. Okay, and you see again the common theme for all of these complexes. We have a large metal in the center and fairly small ligands surrounding it. So in this case, our large metal is the rhenium and our small ligands are hydridoligands. So you see that, well, here's 6 of the hydrogens. These 3 and these 3, they're making the prism, and then there are 3 other ligands. This hydrogen, and that hydrogen, which lie above the square faces of that tri-capped prism. So the tri-capped prism is not the only possibility how to realize the coordination number 9. There are other possibilities. For instance, you can also have a capped square entaprism. An example for this would be the nona amine lanthanum 3+. Coordination number of 9 is not the highest possible coordination number. Coordination numbers up to 16 have been observed, but they get increasingly rare, and we do not have to go through all these examples. It's just, in this case, enough to know that we can have coordination numbers of up to 16. Okay, so this was what I wanted to tell you about coordination numbers. Let us move over to the next subchapter, which is about isomerism. So you probably know isomerism from organic chemistry. In coordination chemistry, isomerism is also important. So let us briefly review the principles of isomerism and how they apply in particular to coordination chemistry. So some forms of isomerism are known in both organic chemistry and coordination chemistry, but some forms of isomerism are also unique to coordination chemistry. So in general, what do we mean by saying, well, two compounds are two isomers relative to each other? What do they need to have in common? In most general terms. They have to have the same empirical formula, but different structures. Okay? The empirical formula has to be the same, but the structures need to be different. So then we can further categorize isomers, so we can distinguish between what is called constitutional isomer and the stereoisomer. And constitutional isomers are isomers that have different bonds between the atoms. So the atoms constituting the bonds are different, or there are bonds between different atoms. Okay, so the bonds are not between the same atoms. Okay, in stereoisomers, the bonds are between the same atoms, but the ligands are at different coordination sites. Okay, so on one bond type, but the ligands are at different coordination sites. So let us first look at constitutional isomerisms. There are several types of constitutional isomerisms. One is the so-called hydrate isomerism, which only occurs in solid state crystals. It does not occur in solutions. So when we talk about hydrate isomers, then we talk about two different compounds in which in one isomer a water molecule is bound directly to the ligands in the first coordination sphere, while in the other isomer, it's not directly bound to the ligand, but it actually exists as isolated water molecule within the crystal. Okay, it would not make sense to define hydrate isomerism therefore in solution, because if that water molecule was in solution, then we would not be able to distinguish from the solvent really, so it would not make sense to call it a different isomer. So here are just a few examples for that. So here we have a complex which is called the hexa-aqua chromium 3 chloride. So what hydrate isomers can we think of that? Well, we can think of hydrate isomers in which one of the or more of the 6 aqua ligands moves out of the first coordination sphere, and one or more chloroligands replace its position. Okay, so for instance, we can think about this compound here, which is now penta-aqua chlorochromium chloride times H2O. We could also exchange more water molecules. So if we do another one, then we would have the tetra-aqua dichlorochromium chloride times 2 H2O. In principle, we could even exchange a second chloro ligand, but for some reason nature doesn't do this, and that leads in this case to 3 hydrate isomers. So here's just one more example. So here we have tetraamine, aqua, chloro, cobalt, 2 plus chloride. So we can move our aqua ligand from the first coordination sphere into the crystal and move chloro ligand into the first coordination sphere, and then we would have, well, the tetraamine, dichloro, cobalt, chloride times H2O. So in this case, we would have 2 hydrate isomers. So I think it's pretty straightforward to understand. So the next constitutional isomerism that I would like to discuss is the ionization isomerism. So in this case, we move one anionic ligand from the first coordination sphere to the second coordination sphere, and another anion from a second coordination sphere, first coordination sphere. So here is an example. So here is pentaamine nitrato cobalt 2 plus sulfate, just also to practice our nomenclature. So we can swap up the nitrate, sulfate, and that gives us then pentaamine sulfato cobalt now plus nitrate, because now the complex has only 1 plus charge. So in this case, we have 2 ionization isomers. All right, so I think this is also pretty straightforward. The next isomerism is a little bit more complicated. So this is the coordination isomerism. And what's more complicated about it is that it requires at least 2 metal ions, and the ligands are bound to the 2 different metal ions. So one example is shown here. So we have here diamine dichloro platinum. So in this case, all the ligands are being bound to a single platinum. So this cannot be the isomer that has at least 2 different metal ions, but another isomer which has the same empirical formula as the compound which we just discussed must exist. And there are actually 2 of these isomers known in this case. The first one is this one here, and the second one is this one over here. So this is the triamine chloro platinum plus amine trichloro platinum minus. So in this case, we have a complex cation and a complex anion, and we have both platinum in the complex cation and the complex anion. So at first glance, it doesn't look like, well, that this compound is an isomer to that one, but when you really analyze the empirical formula, you will see that these 2 are actually isomers. They have both the same empirical formula. Let's just prove this. Well, we have here 1 platinum and 2 amines and 2 chloroligands, and here we have 2 platinums and 4 amines and 4 chlorines. So we have just twice as many atoms, but we can divide this by 2, and then the formulas will be identical. Okay, so now in this isomer, we have the ligands bound to different metal ions. So in this isomer here, we have the ligands all bound to the same platinum. Here, over here, we have the ligands bound to different platinums. So another coordination isomer is this one here. So this is the tetraamine platinum 2 plus tetrachloroplatinate. So in this case, 4 amines are bonded to the complex, the platinum that contains to the complex cation, and the other chloroligands are being all bound to the platinum that belongs to the complex. And again, the empirical formula is identical because also here we have 2 platinums, we have 4 amines, and we have 4 chlorines. Okay, so we can have coordination isomerism in different variations, and I'm just mentioning a couple of those. So for instance, we can have metal ions of different elements. In the previous example, the elements were the same. They were both platinum, but you can also have different elements. In this example here, it's cobalt, chromium. So in this coordination isomer, 3 ethylene-diamine ligands are bonded to the cobalt, and 6 cyano-ligands are bonded to the chromium. And we have a coordination isomer in which it's the other way around. So in this case, the 3 ethylene-diamine ligands are bonded to the chromium, and the cyano-ligands are all bonded to the cobalt. You can have also coordination isomerism with different oxidation states. So for instance, here again, the metals are the same, but in this case, the metals are in different oxidation states. So the element is again platinum. So in this compound here, we have platinum here in the oxidation state +2, and this platinum is bonded to 4 amine ligands, and this platinum here is in the oxidation state +4 and bonded to 6 chloroligands. Okay, so in this coordination isomer over here, this platinum here is bonded to 4 amine ligands and 2 chloroligands. So the oxidation state is in this case +4 because the chloroligands are anionic, and we still have to have a 2+ charge at the cation. So because of that, the platinum must here a +4 charge. And here we have tetrachloroplatinate 2-. In this case, the platinum is also in the oxidation state +4. That's because the anion has a 2- charge. So we have 2 platinums, sorry. The anion must have a 2- charge. So the platinum, so the 4 chloroligands together have a 4- charge. So therefore the platinum actually must have the oxidation number +2 and not +4. Okay, so the oxidation numbers are being swapped up, but that is actually a platinum 2 and not a platinum 4. Yeah, so please correct the mistake here on this slide. All right. Another form of constitutional isomer is the so-called linkage isomerism. And this kind of isomerism requires a ligand that has more than one reactive end. And that requires, of course, 2 donor atoms at these opposite ends. So in this kind of isomerism, energy differences between the isomers are typically small, so a ligand can switch its reactive end fairly easily, and that can depend on minor differences in the environment in which the complex is. So, for instance, the solvent can play an important role. So here's an example. Thiocyanate is an ambidentate ligand. So both the sulfur can bind to a metal, but also the nitrogen can. And which end the ligand uses depends on certain factors, for instance, solvent in this example here. So here we have palladium complex in which we have here two tris phenyl arsine ligands and two cyanato ligands in which the sulfur is being used as the reactive end. And here we have the respective isothiocyanato ligand. We call it isocyanato when this ligand uses nitrogen as the reactive end. So now in an apolar solvent, this form here is preferred. In a polar solvent, the thiocyanato version is being preferred. So we could speculate why. We don't know exactly why, but one possibility would be, for instance, that nitrogen is actually the more electronegative element, so it can make more easily hydrogen bonding with a polar solvent. Therefore, in a polar solvent, the nitrogen points to the solvent and the sulfur points to the palladium, while in apolar solvent, the energetics are the other way around. Okay, it can even be that within the same complex, the ligand binds in different ways. And one example is shown here. So in this example, we have again a palladium complex. And you see we have two thiocyanato ligands. One binds with the nitrogen, and the other one binds with the sulfur. We can think about why. And when we analyze the steric environment, we realize that, well, we have here two nitrogen donor atoms at this bidentate ligand here, but I see that this end of the bidentate ligand is significantly bulkier than this end here. So when the thiocyanato ligand binds with the sulfur, it can actually bend away from that bulky group because it has two electron lone pairs here at the sulfur, which are sterically active. Whereas this is not the case when the cyanate uses the nitrogen. Okay? And so it utilizes the nitrogen when it can, okay? When there are no bulky substituents here at this nitrogen. But over there, it's just no longer possible. So it has to use the sulfur in order to be able to bend away from the bulky chemicals. All right, so thiocyanate is not the only ligand which shows this ambidentate isomerism. There are also other examples, for instance, nitrite. So the nitrite can either use the nitrogen or the oxygen for binding. When the nitrogen is being used, we call it the nitroisomer. And when we use the oxygen, we call this the nitritoisomers. Nitritoisomers usually are being more stable. All right. So these were all the constitutional isomers that I want to discuss. Now let us go to stereoisomers. We distinguish two basic kinds of stereoisomerism. You probably know this all from the organic chemistry. So which are the two kinds of stereoisomerisms that we know? Enantiomerism is one form.
What about cis and trans?
Sorry?
cis and trans.
Oh yeah, it went away. Okay, so one is called the enantiomerism, and the other one is called the diasteromerism. So what's the difference? So now when we have two enantiomers, then these are mirror images from each other that cannot be superimposed. And that means that enantiomers are always chiral molecules. And remember the definition of chirality: a molecule is chiral when it does not have an improper rotation of flexion. Okay? That includes a mirror plane, which is in S1, and an inversion, which is in S2. Okay? Only proper rotations in the identity are allowed. So everything which is not enantiomers is diastereomers. Okay, so these stereoisomers are not mirror images to each other. They may be chiral or not. Okay, when one of the two diastereomers is chiral, then that means that there must also be an enantiomer to it, because there must be a mirror image to it. Okay, so here's just an example from organic chemistry to review this. So here we have ultra-triic acid shown in the Fischer projection. So in the Fischer projection, we can have the first OH group pointing to the right and the second OH group pointing to the left. So how does that translate to the real structure, which is seen here? So here we see the real structure, so all the carbon atoms lie within the paper plane. And an OH pointing to the right means, well, the OH actually points toward us, and the OH and OH pointing to the left means that the OH is actually pointing into the ball plane. Okay, then we also have the beta-triic acid, where the orientation is the opposite. So the first OH points to the left, and the second OH points to the right. So what is the real structure? Well, the real structure is then that the first OH points into the ball plane, and the second OH points toward us. So now these two isomers are enantiomers, and that means that there must be mirror images to each other which cannot be superimposed. So it is easier to see that these two are mirror images to each other when we actually rotate this isomer here by 180 degrees around the carbon-carbon bond. And then the two carboxylic acid groups here point to the left. And this OH group, which formerly pointed into the bond plane, now points out of it. And this OH group, which formerly pointed out of the paper plane, now points into the paper plane. And now you can see that the resultant molecule here is a mirror image to this one. Okay, we can place a mirror plane in between the two molecules. Note that this is a mirror plane which is not part of a molecule. It's not a symmetry element. It's a mirror plane which you would place in between the two molecules to show that the two are mirror image to each other, just like my left hand and my right hand. Okay. Put a mirror plane in between. Okay, so now we have a third form of tetraic acid. It's called the mesotriic acid, in which both OH groups can be drawn to the right side. Okay, so that would mean that both OH groups point out of the bond plane. So now it's easy to see that this form of tetraic acid is not a mirror image to the other two. Okay, therefore, this would be a diastereomer relative to the other two. Okay, Now, at first glance, it seems that we can also draw a mirror image to the mesotartaric acid. Okay, we can just draw it, yeah, and then the two OH groups would point to the left. But note that this is not an isomer because we can just rotate one of the two molecules by 180 degrees around the carbon-carbon axis, and then they superimpose. And when two molecules can be superimposed, they are identical. Okay, so therefore, these molecules here are identical molecules, but they are not isomers to each other at all. Okay, so then the presentation is over, and I think we can just stop at this point, and we can just continue in the next class with examples of their isomerism in coordination chemistry. I can just stop here.